Hey guys, I'm down a soundtrack here just to make sure that everything is okay. I've been having technical issues recently, so I need to make sure that things are working properly. If you can listen to me, please say something on the chat. I'm also trying to double check things here, okay? Hey guys, uh, down a soundtrack here just to make sure that everything is okay. Okay, let's start. So, if you experience any technical issues, well, you let me know in the chat, okay? So, let me start by introducing myself, as I usually do. My name is Leonardo Bezerra. My GitHub is Leo Bezerra. And I'm a researcher, developer, and professor, used to be in that order, at Instituto Metrópole Digital, which is an institute here at Universidade Federal do Rio Grande do Norte. If you want to check, go to Google Maps and you find Natal, here in Brazil, and you see my city, okay? Well, I usually don't show the pictures anymore. So this is where I live, this is where I work, and I work as a professor here. And I teach basically two sets of courses. One is called, well, there's some technical issues here. Let me check the connections, just a minute. Okay, let's see if things work better now. Okay, so as I was saying, I'm a professor here at the university, and I teach courses on computational thinking and problem solving and programming in general, and these are represented here in my GitHub through Python 0, Pensamento Computacional, and Python TADS. These three repositories are in Portuguese, but I teach a second set of courses which are based on data science and machine learning, and in these cases, the repositories here, two of them are in English, which are Pandas 0, the one we're going to use today, and Scikit 0, the one I'm using for the broadcast on Thursdays. So just a reminder, on Mondays and Wednesdays I run some broadcasts at in the evening here at Brazilian time, and they're in Portuguese. So if you're in Brazil, they run at 8:30 p.m. And on Mondays it's on Python, like a computational thinking with Python using Python 0. and on Wednesdays using Python TADS, which is for problem solving, also using Python. And on Tuesdays and Thursdays I'm running these broadcasts at this time because it's a bit more international, more universal for everybody. They're in English, as you're seeing, and data science with Pandas is done on Tuesdays. Machine learning with Scikit is done on Thursdays. Okay, so just a note on this: even though all of these repositories use some sort of Python environment, that's just to make the things easier, so you don't have to worry about understanding complicated programming language. I use Python as things should be kept simple, and Python helps a lot in that sense. So let me show you Panda 0. So, by the way, so when it comes to Panda 0, there's an English version and a Portuguese version, right? So in the English version, let me show you here. Oh, okay. So there are some topics here, and then I always introduce this course saying that, look, there is the idea of a graphical user interface app that you can use, like Orange 3, or command line interface tools, like we're going to use it here. So what we're going to use is a mix between both. So we code in Python, even though we're not really depending on programming logic, and we visualize things almost as if we had a GUI, okay? It's not exactly the same thing, but it's quite close. We do that in Colab, which is an environment for programming, interactive programming that Google made available. So it's based, Colab is based on Jupyter notebooks, which you can also launch in Binder. But here, to make things simple, we're going to use in Colab. If you missed the last broadcast, you can see them on YouTube. So the badges are here for the previous two. Almost all of these posts here have been organized originally by a student, and they were originally created in Portuguese. Now I'm translating them to English, so other people are helping translate them to English. So the references are here, the credits. We're going to run this one, data and presentation, and we are in the major topic called meeting pandas, which basically means that we heard there was a first step video just to understand the basics on pandas. Data frames as databases meant to discuss queries, and I spent the whole video saying queries because in Brazil we tend to think it's called queries. So finally I learned my lesson. We were seeing how to query the data. And here we're going to do data analysis and presentation, which basically is, let's see how to compute some descriptive statistics about your data and how to visualize that. Okay, so let me launch Colab here and welcome everybody. When you're joining in, feel free if you want to say where you're from. It's really nice. Just say hello in the chat. For me, I really prefer to be talking, to be interacting, than just to go over. Okay, so just for you to see the table of contents here. We're going to discuss a bit about invalid or missing data. We're going to talk about a bit of descriptive statistics like central measures and dispersion measures. And we're going to also discuss a bit of data presentation. We're going to see histograms and some kinds of distribution plots like box plots and value plots. Okay. So going forward with this, preparation for analysis. So when you're talking about analyzing data and exploring data, you basically depend on understanding the data, what type of data you have, okay? So let me start with this. You have here either numerical data or categorical data, okay? So let's start with numerical data. They can be referred to as quantitative data, and they can be discrete if you're talking about things you count, or continuous if you're talking about things you measure, okay? So age, weight, and height would be prototypical examples here. Categorical data is also known as qualitative. They usually don't represent numerical characteristics, but there's a difference here that in the case of ordinal, you might have an order between those categories, and in the case of nominal, there are really no orders. Okay, so ordinal reminds me of ranking. So when you can rank something like stages of a disease, or then you're saying that you're talking about category ordinal data. Okay. If you cannot do any kind of ranking, then you're talking about nominal data. So that's what you have mostly. And let me go back here. So if you want to more into these topics, you can check this video. It has some nice explanation on this. But once you have understood the basic types of data that you can come across, one thing that you should know is that data won't always be there. So invalid or missing data is something we should talk about. And IBM Data Analytics has this statistics that 80% of the time spent on a data set is spent in cleaning up the data. So this process of starting the cleaning up, the data wrangling in general process is quite time consuming, and you should be ready to do it because you don't go anywhere without this. So let's start with Pandas, okay? So every time you run something for the first time, you have to say run anyway, because this notebook was not authored by Google. The first time you try to run a cell, it's going to connect to a computer in Google's infrastructure. So you don't get a whole computer for yourself, although you're going to believe it is. You see here, there is random disk. You think it's a computer, but it's what we call a container. It's a virtual machine. So it looks like a computer, but it's a simulation of a computer. So a single computer can host several of these simulations, several of these containers. In terms of privacy, it's good for you because basically you're safe that other people will not have access to your data, except for Google, but other people running will not have the same thing. Okay? So if you missed the previous broadcast, we're importing Pandas here. We're using a name called PD, so everything we use from Pandas will have to be referred starting with PD, so like this. I want to read this file, so this is the data is in this GitHub repository. It's separated by commas, and I intentionally am making this explicit here. Let me read this. I'm going to get a data frame from that, and I want to refer to this data frame as missing data. So I'm associating the name missing data with the data frame that I read using the read CSV procedure, okay, method. So missing data has these characteristics. Okay, we can see that it's like this. So let's see something that is interesting here. So when Pandas identifies something as missing, it will use this, NaN. Okay, so not a number. That's how Pandas refers to missing data. So we can check those using the is and a. Okay, and then when we run this on numbath, for instance, so numbath would be this one. There at index 3, there is a missing value, so index 3 says true. Okay. Now, if you want to check for the whole data frame, we're not going to do this one by one. What we do is that we use is and a straight from the data frame, and we use the method sum to say please sum up for all the features, and that's what we're going to get. So there's one missing value for the ID. I think it's properties here. Yeah, so property ID. 2 for street number. 1 for I think it's owner occupied. 2 for number of bedrooms. 1 for number of bathrooms, and 1 for square feet. It isn't always going to be the case that Pandas identified invalid data. So here in num bedrooms, there is this NA here, and it's meant as a missing value, but Pandas could not identify this. So if you want, and also square feet had this, which was also meant to represent invalid data, missing data, but it's just invalid, right? So this should be missing, but it's invalid, should be missing, but it's invalid. So let's see this. If we use unique and non-bedroom, so you can see all the possible values there, and you see NaN, NaN stands for not a number, which means missing value, but NA is being treated as if it were a text, okay? So we can also see this because of the type of the feature, which is object, which means that they could not switch it, Pandas could not parse it as a number, and it should because it's 1, 2, 3. It's clearly supposed to be a number, even the name of the feature says that, but it could not because of this NA here. For missing data, we can do the value counts, and you're going to see this. When we do value counts, you can also say drop NA equals false, and it's going to show if you have any NA. So there was one missing value, okay, it shows up here now, but this one is not being considered a missing value. And the dynamic type here, it's okay, this is for value counts, but if I show, let me see here, if I do this, and I check its type, D type, we're gonna see that it's an O for object, okay? So it's been considered an object because you could not parse it as a number given that it had this, okay? The other thing is that the data might be invalid when it doesn't respect the domain of the feature. In a sense, this is happening here. It should be numbers and it's not, right? But let's see, this on occupied, it should be yes or no. You see? Yes, no, 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 and then 12. Ooh. Nan makes sense because it's a missing value, but 12 shouldn't be here, okay? So let's see what happens here. If I ask this, you're gonna see yes, no, 12 and not and a missing value. We can use the useIn method to check if the data there respects a given domain. So the domain is a list. In this case, I'm giving y and n, and I'm getting all the replies here in domain condition, okay? So just for you to understand what's going to happen, we're going to have a lot of trues and falses. I'm just showing the beginning of the series. So this series is being transformed into a lot of trues and falses, okay? It's true if the value is in this list of options, it's false otherwise. And since what we can do is that, okay, if I just say head, I don't know if I have a false or a true value here, but we can use the all method from Python to check if everything is true. The all will return true if everything is true. And in this case, returns false because there is someone here who's not respecting the domain, okay? So, okay, I still want to identify which one is not abiding to that. So I take domain condition, everything was true, and this one was false. If I use this, I'm gonna see all the ones but this line. Since I only want to see this line, I'm gonna invert the condition. When I use this symbol before, it's called the not operator, every true value becomes false and every false value becomes true. So I'm only gonna see the 3, okay? So yep, row number 3. Actually, the not a number is also an example of this, of not being yes or no. So it also shows here. So I see 3 and I see 6, okay? Oh, this was the first thing I wanted to talk about. These are called data types, invalid and missing data. I usually take these transitions between sections to ask if you have any questions. If anyone has a question, please, you can post it in the chat. And it usually takes like 15 to 20 seconds for me to see the things because of delays. So please, if you have any questions, I'm gonna see it in like 15 or 20 seconds, which is by the time you're gonna listen to what I'm saying and you're gonna write your comment. So I'm gonna move on to the next section, but when I see your question, I'll stop and I'll answer, okay? So let's start the analysis. So it's not that we didn't start, but anyway, let's, I think the idea is starting the analysis because we're gonna switch to a different data frame, which you're gonna use for the rest of the tutorial. So we're gonna get this data. So let me download it here and load it and see what is this. I have a lot of entries. I have a country, the records for several years, and in those records I have the population size, the continent to which it belongs, the life expectancy in years, and the GDP per capita. Okay, so you're seeing that we expect that the life expectancy will grow in every country, right? Since the life conditions have improved, even if they still need to improve a lot. This could be affected by war and this kind of stuff, but you see Afghanistan, which had a lot of problems with war and all these kinds of things, and it's still the life condition is improving, so they can improve a bit slower, but they're still improving. So let's take a quick look at the data types. We do have data D types, okay? So country is an object, year is a integer number, population is a floating point number because there's this .0 here. For some reason someone decided to provide it like this. Sometimes these numbers don't come in absolute values, they come as like in million per million of inhabitants, like 8.4 would represent 8.4 million inhabitants. A continent is it's considered as a string, as a text, okay? Life expectancy is considered as a float, GDP per capita as a float, so these two are real valued numbers. This one is being interpreted as real valued because in the original data there was this 0.0 Otherwise, it would be interpreted as an integer. If I wanted to convert it, I could also do that. Okay. Let's see how many value counts for each continent. Well, it's a lot, but we're seeing here that every country has repetitions, right? So we're seeing a lot of this. If I'm not mistaken, there are like 12 values for each country. Let me see if this is the case. So if I want to see that, how do I do it? I'll take a country and ask for value counts. I think there are 12 for each. Yeah, so there are 12. I think it's every 5 years. So it started in 1952. 12 times that would be 60. So we would have 2012. Let's see if that math checks out. So I have 12. 2007. Okay, so something in my math didn't check out. Oh, if it's 12 values, I just make sure here. Yeah, so it's up to 2007. Okay, so it's from 1952 to 2007. Well, let's move on. So we have all those 12 values here. In this case, it's like an ideal situation. There are no missing values, no invalid data. It's awesome, but it's not. That's not really real world. Anyway, let's assume that we've come to a point where the data has no more missing values and no more invalid values. That would be awesome. And if we assume that, we can start with. Sorry, guys. We can start with descriptive statistics. Okay. Pandas offer the main central and dispersion measures. We can apply this to numeric data series. So if you're not familiar with that, the mean is basically the sum of all points divided by the number of points you have. The median is the value that splits the intervals, the ordered values in half. Okay, so half of the values stay before the median, half after the median, and the mode is the most frequent value. Okay, so if you talk about distributions like this, you would say this situation. Let's see the mean. The mean for the numerical values are year, pop life expectancy, GDP per capita. So the mean for the year doesn't make much sense. The mean for population, it's a lot. So it's around, I think it's 2 million or 29 million. So if I add 6 here, I think it would be 29 million. Okay, which makes sense. Life expectancy would be 59.47. That's quite good. And then GDP per capita would be 7. That should be in, I don't know, millions of dollars maybe. So 7,215. So $7,215. That would be too low. So $7,215. That would make more sense. So let's see the median. The median for the year is 1979.5 because that's the way it's computed. And the mode, the most frequent value. So for a year, they're all the same. There are 12 occurrences for each country, right? So if you multiply times number of countries, you have the number of occurrences. Dispersion measures. Okay, so how are the data distributed? So variance is this, and for this I really recommend StatQuest, which is a YouTube channel that discusses this very, very well. So the variance is basically you take all the points. For each point you compute the distance between the value and the average, and those distances you take an average of them. Okay, so the thing is that since you don't want positive and negative distances to cancel each other out, all those distances are taken squared, and when you sum everything you get something that doesn't make much sense. We were talking about years, and then the variance is 298. Of course, there are not those many years in there. Okay, so standard deviation tries to fix that a bit. It's the square root of the variance, so it brings things closer to the range we were talking about. So 70.26 years. So this makes a bit more sense than this, right? So this would be a measure of dispersion. Another measure of dispersion is what we call a quantile, which basically, like the median splits the order data into 2 equal sized intervals, like 50% of the data is before, 50 is after, If you're talking about other quantiles, like the 25% quantile, you're saying that 25% of the data is smaller than that, and the remaining 75% of the data are larger than that. Okay, so quantiles such as 25, 50, and 74 are so known that they are known as quartiles. Okay, quartiles can be referred to as first, second, and third. The second one, which is 50%, corresponds to the median. Okay, so the 25% quartile or 25th quartile, quantile. This is the first quartile. Okay, so when you're talking about quartiles, you're talking about first, second, and third. When you're talking about quantiles, you're talking about the quantities. So the 25th quantile. Let's see, the first quartile here would lead us to years below this. So we have all the data for each the years below this quartile. Okay, the first quartile. Let's see the shape of the whole data. We had 1704. So yes, it makes sense that a fourth of the data is here. Okay, we can check for other quartiles. So the second quartile would be the one we already saw before, right? Where was it? So it is median. Okay, here. And then we could get all the data here, and it should be half the data. Oh, sorry, forgot to uncomment this. Half the data would be this. Okay, so this 25% is smaller than this. This is the 25% that is smaller than that value, than the 1965.75 value. These are the 50% that are smaller than this quartile here. Okay, if we use describe, we're gonna get all of this together and also count mean and standard deviation, like count mean, standard deviation, minimum, maximum, and the 3 quartile. Okay, so the minimum value here for a year is 1952, the maximum 2007. And then the variance is not here, but the standard deviation is. As I said, the scale of the variance is a bit off what we were talking before, so it doesn't make much sense that you use the variance in here. Okay, you use the standard deviation as a measure, as an indirect measure of variance. So this, if I do data.describe, all of the numerical features will get described like this. Okay, so the count of all values, the mean for all values, for all features, and so on. So the number of distinct values, you can get them with n unique. It's quite reasonable sometimes. So there are 12 years, 142 countries, the values for the population. Okay, this makes a lot of sense when you're talking about categorical values. It doesn't make much sense when we're talking about numerical values, right? Year here is being considered a numerical value, but you could consider it just as an ordinal feature, because anyway, the reasoning there is a bit different, right? So it doesn't make much sense that you're talking here, let's say the mean year or something. Okay, you want to know the range. And usually we're talking about daytime. I don't discuss much daytime in these notebooks, but if you go later on to the time series notebooks we're going to be releasing soon, you see that daytime makes a big difference when we're talking about time series. Okay, so if you only see data, I can also apply n unique to a single series. Okay, and we can sort the values. We can sort the values like this. First, I take a single series, sort the values, and I get the first ones. The sorted values are also a series, right? And I take so I can use any method from a series in Pandas. If I take just the head, I'll get just the 5 first ones, which would be this. They're all 1952. Okay, I can do that by multiple values, by multiple features, and I can also say ascending or not. By default, ascending is true. Here I'm setting it to false, so it's going to be by year, so descending in year, and also descending in country. The idea is every time you have a tie here, the next criteria, the tiebreaker is this. Okay. Here, if I had made it true, year and life expectancy, I would see ascending year and ascending life expectancy. So Afghanistan was in the worst situation from this data in 1952, even worse than Gambia, which by its turn was worse than Angola, Sierra Leone, Mozambique, This is impressive. I had no idea how Afghanistan was in a bad shape. Well, so again, I'm going to take a little break here to see if there are any questions in the chat. If you have any questions, as I told you, there are like 15 to 20 seconds of delay. You can pose the questions there, and I'll answer as soon as I can. And again, not everybody watching this speaks English like as a native language, as the first language, but that should not be a problem, okay? Don't feel ashamed of asking questions because English is not your first language, okay? Anyway, as I told you, since there's this delay, I'm gonna move on. And if there's something you want to see that I didn't answer here, you ask. As soon as I see the question in the chat, then I'll try to answer it, okay? So we were discussing in the beginning, let me show the table of contents here again. We were discussing the basic data types, right? Sorry. Let's see if it comes up. The basic data types, especially a special discussion on invalid and missing data. Which comes back a long time from here in Scikit 0. So if you were watching the Scikit 0 series, you saw these last week or no, a couple weeks ago, and it's available in Scikit 0, how to deal with invalid and missing data. Here we're not going very deep into this, we're just showing that you can identify them. So that would be called data imputation, and we use it a lot when we're talking about machine learning. But for data science, sometimes you need to keep the data missing because it's sparse data or something, okay? Now we're talking about descriptive statistics, and this is important because you need to understand what they are. Of course, I went a bit fast on this, and if you want to understand them more, you can go to StatQuest and see a video on each of these topics. I just wanted to show how to visualize them in Pandas. And now we're going to data presentation, which basically means I'm going to be showing you how to visualize this, okay? So we're going to talk about histograms and other kind of distribution plots. So the very basic, let me just fix this. The very basic library we use in Pandas to visualize things is called matplotlib. And the problem is that matplotlib is really historical in the sense that it inherits a lot of things from the mathematical plotting libraries that existed for many different environments, like for different programming languages. And that's not very Pythonic, and it's not very simple. So the guys that proposed Seaborn made an excellent work of making a higher level approach to matplotlib. So we're always going to be using matplotlib here. Most of the times you can just import Seaborn as SNS. This is the convention. Eventually you might import matplotlib.pyplot, which is the default module we get from matplotlib, and the convention is to call it PLT. Okay. And then every time you import Seaborn, we recommend that you set its default configuration as the standards for whatever you're using, okay? So that's why we use sns.set to say, please apply your default configurations to the plots, okay? Histograms, let's see what's going on here. So if I want to do it straight from a series, I can just say hist and then the number of bins, and this is what happens. I'm seeing a histogram, okay? Because I've added the configuration from Seaborn, it shows a bit differently from what it would show in matplotlib, if you have ever tried that. Histograms are basically stacking up the values, and since, for instance, for real value data, it's very difficult to have the same data repeated, we cut that into bins, we cut the whole interval into bins. And the idea is that we're stacking the values that fit in the same bin. Okay, so with 100 bins, that's what we have. If we go for 2 bins, we get this. So we split the interval in half. All these 600 values fit the first half. All these probably 1100 values fit the second half. Okay. Of course, this doesn't tell me much. And then I could do that with 1,000 bins, which is the other extreme. It's so many that I don't see anything. So the basic thing I recommend is that you don't set the number of bins. You see what's there, and you start checking this and testing this as a function of what you know from the data or what you're seeing from the data, okay? So for year, for instance, I'm gonna give 12 bins, and they're all the same, okay? That's exactly a uniform distribution example. So you have the same probability of finding a given year if you're doing random sampling, because they come in the same number of occurrences, okay? That's a characteristic of this particular data set. It's not very common in practice, but still. If I do value counts, what I've shown before, it's 12 for each. Actually, there are a number of countries here, and because of that, since they occur 12 times, you have this result here, okay? If I want to configure this a bit, I can set a lot of things. I can set that grid to false. I can change the label size on both axes, X and Y. I can change the label title and the font size for those. I can change the title of the plot, and that's where PLT comes handy, okay? Because the configurations can be adjusted straight from PLT. I can even change the range of the X axis. Let's see here. Before it was starting at, let's see, it was starting at close to 0, I guess. And here I'm saying start at 22. I don't see much difference actually, but still. I set the grid to false, you don't see the grid anymore. I've changed the sizes, I've changed a lot of things here, the font and stuff, the title. Well, that's this kind of customization that you can do. This is very convenient because you plot it straight from the series. But if you want something more powerful, you can use distribution plot, this plot from Seaborn, and the way to call it is this plot and then the series, and I can use the rest as I did before. So this is more interesting in the sense that the plot is trying to make a regression here to say, I think this is the probability distribution for these data, okay? And then let's see here. The values are here, so of course they don't match exactly what we had before, mostly because we have a distribution here that has 2 peaks. So if I check for the mode, I would see the mode around here, but you can see that there's another mode here, but it's like a second mode. Let me print here, median mode and variance, and we're gonna see this. So median is around 60 is around here, and mode is around 69.39. 69.39 would be around here, okay? And then the variance is like this. So the standard deviation makes more sense, right? The standard deviation is around 12, the variance is 166. It doesn't make sense that the variance be 166 if you consider that the values go from 0 to 90 something. But still it is, because we're taking square differences, and in the case of the standard deviation, we bring them back to the same scale. Now I could have also plotted there a fit, which is a distribution of reference. So I'm going to give you the normal distribution. I can get a method that generates a normal distribution from this SciPy stats module. So I import this, and I can say, please take that data and compare to this distribution that I'm providing you, which in this case is a normal distribution. So the black line represents the normal distribution that fits this data. Like the mean would be here, the standard deviation would be like this, right? But what we actually have is the blue one, or at least the blue one is the best approximation that the plot is giving us. And this means that we don't have a normal distribution. We can have done this GDP per capita. Let's see GDP per capita to see what happens here. Sorry. Let's run this. See, GDP per capita follows what we call a logarithmic distribution. Let's see. If I try to fit a normal distribution, no, it doesn't make sense. Okay. So this one that has these two humps here, we call that a bimodal distribution because it has 2 modes. Okay. And this one, we call it a logarithmic distribution, or actually the correct would be exponential distribution, because the decay is exponential in this case. We start from we can also call it a long tail distribution, right? A tail distribution for short. Let's see where that comes from. Let's isolate the data from Africa from the data in Europe, and let's plot them in the same plot to see what happens. And notice that just because I'm giving the two commands in a row, they're showing up like this. So this is Africa, this is Europe. Life expectancy, and I'm sorry, but this is too much for me. This is socially extremely impactful. That in Africa, for the data that we have there, the life expectancy goes around here. Basically, people are having half, or kind of like half the lives of people in Europe. I live in Europe. I've been to Africa, and the math doesn't add. I really like the fact that Europe has learned, as a social democracy, how to try to help and provide a welfare state for people who are in the system, but still it has a lot of inequality with people that are outside the system. But still, much of what was built for Europe was built upon Africa, and it's very hard for me to see this kind of plots. So I really hope that we can see Africa shift in this direction, and that people in Europe be the motors of this change, for instance. And us too, right? Don't leave the blame only to others. We can also see other kinds of plots here, so box plots. For instance, let's see a box plot. And what's a box plot? A box plot is a summarization of a distribution based on quantiles, right? Actually on quartiles, to be more specific. So we have the first quartile, second quartile, third quartile here. And the distance between the first and the third is called the interquartile distance, right? And based on this distance, the box plot computes what it considers to be the minimum and the maximum value, which are the whiskers of the box. And any value that are outside this will be considered outliers and are represented by points. So every time you have a box plot, you have all that information there. The minimum and the maximum according to interquartile distance, and then the outliers, which are out of that range, outside that range, and then the first, second, and third quartile. Sometimes you're not going to be able to see the second quartile if it matches the second or the first or the third quartile, okay? So Africa is really down here. Asia is a bit all over the place. Americas are also very spread. Europe is kind of very well, and Oceania is even better. But we're talking about many years really, right? Let's say this if we just take a snapshot for 2007. Let's see just for 2007 what happens. And in 2007, so here we were talking about Africa from 42 maybe to 50, maybe 53, 54, okay, from 42 to 54. Here we're talking about Africa from 48 maybe to 59, which is already a great improvement. But see, 48 to 59 keeps Africa here. And here Europe was already from 70 on, okay? So that's a way to see the differences. And actually here Europe is from 75 maybe to 80, and the median is very close to the third quartile. That's how you see how the life quality in Europe is gone. I mean, there are many Europes, but still. And that's probably the reason of this. Probably this is Eastern Europe, and this is Central Europe, right? And even Northern Europe, like Scandinavia and this stuff. Oceania is, well, the variation in Oceania, there are not many countries there, but still it's impressive, right? So I didn't get to check which countries are for Oceania. So let me just check for us to see. So let me query the data. Say continent equals Oceania, and then let's see what happens. New Zealand and Australia, I guess these are the only values. Let's get just country and ask for unique values. Yep, that explains a lot. Add all the other Oceania countries there, and you're gonna see that it's not that beautiful, but still, if you're only talking about Australia and New Zealand, Yep, probably living there would be something very nice. Okay. Well, these are box plots, and we can also have violin plots. So box plots are trying to show us the distribution based on the quartiles mostly. Violin plots are actually giving us the distribution. So they actually show the shape of the distribution. So in Europe, there's this hump, as I discussed before. So probably most of the countries that are here should be Central and North Europe, and the countries that are here should be Eastern Europe. Asia is all over the place, from East Asia, Central Asia, South Asia. I'm not pretty sure where they would stand here, but you could check this. Africa is also has a multitude of Africas, like South Africa, the south of Africa, the north of Africa, the Sahara region. Americas, I mean, you talk about North America, you're talking about mostly Canada and the US, and many of the statistics on Mexico are pulled up by them. You talk about Central America, you're talking about so much poorness and poverty and inequality. And if you're talking about Latin America, you're talking about everything, really. South America and Latin America. And then Oceania has this big concentration here because we're talking about two countries, right? So when I first learned about violin plots, I thought this was awesome because it even has the box plots inside. Can you see the box plots here? So the dot, the white dot is the median. The tips, like the edges of the box, are the quartiles. You have the mean and the maximum. Like everything is here. And I was asking, so everybody uses this, right? And the guy who introduced me violin plots was saying, yeah, everybody should use this. It's been 10 years and nobody uses violin plots. I have no idea why. Maybe because, I mean, people have a hard time interpreting this, but I really like it. I really like them. So people prefer to just plot the box plots and then the distribution plots. And but still, that's what they want, right? So just for us to compare this to this, we had the same plot here, the distribution plot for this. You see the little hump here, and then the rest of the data is here. This is the for Europe in 2007, or no? Where is Europe for 2007? Ah, okay. So let's plot Europe for 2007. We'll take this because I want to reproduce the same plot here, just with the data for 2007, to see if we had an improvement there. So I already have Africa data. What I'll say is that Africa data is now going to be for year. Actually, it's better that I just take data 2007. Okay, so data 2007 with this, and then I'll plot this and let's see what has happened. Yeah, you see Europe, this has this little hump here. So some countries, if this impossibly large, I would be really interested in knowing which are these countries, and I would expect them to be Central Europe and Northern Europe, and the countries here would be the ones that are Eastern Europe. Let's see if this really holds out. How do I know how to split the distribution in half? I hope you remember that. Europe data, and I'll take life expectancy, and I want the median. So the median here, Europe data, and that's it. And if I say I want Europe data, where this, is smaller than the median, this is another way of querying, okay? So now I only have the data for these countries. So the ones that are under, let me get the, so this is becoming a bit big, right? So below median, this, and then I want to get from below median the countries and the unique values, and they should be in mostly like Eastern European countries. Let's see if this holds up. Albania, Bosnia, Bulgaria, Croatia. So the countries that would surprise me, I think it's Denmark. I'm surprised by Denmark here. Most of the other countries I would have expected that. Even if I've been to Slovenia, the quality of life there is impressive. Czech Republic also looks like a great place to live, but still you see that it has a lot of inequality. Portugal is like a very small country in Europe. And then you can do the same and take the So let me do this in a different way, which is a bit more easier to visualize. So I'll say that Europe median equals the median for life expectancy, and I'll say that I want to query all the cases in which life expectancy is above Europe median. And you remember this, right, from the previous chat? We use f strings. Everything under curly brackets will be replaced, will be treated as a name, and we replace it by the value it is associated with. And this would be above median, and I want to see what happens here. Yeah, so these are Central Europe countries and the Scandinavian countries. Northern Europe, right? Because Iceland is also here. So yep, I've seen that reality in person, and it's true. That's why I think I got the guess right. If you ask me about Asia, I wouldn't know how to split it very well. If you ask me about Africa, I think South Africa would be here, but I'm not pretty sure. I would not know who is around here, so I think around here would be, I know South Africa, I don't know any other country that I would consider to be in this region. Well, you're invited to query the data and check for yourself. Now you know how to do that. I hope you have found this broadcast interesting. Again, if you want to ask something, I'm available. Please wait for 15 to 20 seconds for you to comment something on the chat. And in that meantime, I will be checking which countries are this, because I'm really curious. So countries for which life expectancy is above 70 maybe. So let's see. And then drop your questions at the chat. So I want to see Africa above 70. I'll put above or equal. It doesn't have to be an F string because it's just that. And then I want to see what are the countries. I would guess South Africa, and I really don't know. Okay, makes sense. Egypt is here. Morocco. South Africa is not here? Ooh, that was a surprise. Ooh, that was a surprise. Mauritius, Morocco, Libya. Dude, I had no idea. That's how little I know Africa. I mean, I've been to Africa, but not to the continent. I've been to Cape Verde, Cabo Verde, and there, of course, it was a very difficult situation. So who's here? Yeah, South Africa is here. I would expect a lot of these countries, but not South Africa here. Impressive. You can check this if you want by yourself later. So they're not in this hump. Okay. What is the life expectancy in South Africa? So that's what happens when you start learning about data science. You really want to know, right? Query country equals South Africa. You start learning and you never stop. South Africa, 49 for 2007. Oh my god. I had no idea. I mean, apartheid is a bit before that. Okay. Well, I'm shocked, and I need to end the broadcast. Thank you a lot for being here. I'm still gonna be, if you want to check this topic, check this very nice presentation. It's known as Gapminder TED Talk. Maybe like this you'll find it. Hans Rosling. I mean, this is so amazing. Please check this. And you can find posts on how to do this on Python. It's very easy. You use Pandas and probably, if I'm not mistaken, Plotly. It's super easy. At some point, you're gonna be seeing things here in this broadcast who got you to the point of being able to do that. Okay. So thank you a lot for being here, guys, and have a nice week. Remember to come back here on Thursday for Machine Learning with Python. Okay. At the same time.